Hello and welcome. In this video, we're going to take a look at combining two functions together that may have different domains. So we'll take a function f, take a function g, and we'll combine them together. And we could start off with some algebraic ways of combining functions with addition, subtraction, multiplication, or division. But then we'll take a look at a more unique circumstance of how we might combine functions and have one function rely on another. Well, let's take a look a little bit at maybe a way to illustrate the domain of these functions. So let's start off with a function f and a function g, where the domain of f is a and the domain of g is b. And these being different functions, they could have unique domains. They may not be the same. But if we wanted to combine functions together and we wanted to plug a single value of x into a combination of functions, we'd have to make sure that x is in the domain of f, which is in the set A, but also is in the domain of G. So it would have to be in the set B. So anytime that we're looking for a combination of functions, whether we're adding, multiplying, dividing, subtracting these functions together, we're going to have to make sure that when we pick x, it needs to be a value of x in both functions so that we can work with the combination of results. Now, this region here that you can see is the overlapping region of A and B. I'll just shade that in. This purple region, the values of x that are in both domains, we call that the intersection of A and B. The intersection of A and B, written A with this little cap here, it's just upside down union. A intersection B is the set of all elements x, where x is an element of A and an element of B. So it's really just this overlapping region here in purple. Well, if we are picking values of x that are in the domain of f and g, then we can do some interesting combinations. Well, make a little table here of some new notations. Whenever we use the notation f plus g of x, what that really means is x must be a value that we can plug into f and g, and we add those results together. So this is equivalent to f of x plus g of x. And looking at this idea above here with our little set diagram of domain A and domain B, if we wish to compute f of x plus g of x, then x will need to be in the domain A and in the domain B, which means that x must be in the domain A intersection B. Another new notation, if we ever write f minus g of x, then that is equivalent to saying take the value f of x and subtract the value g of x, assuming they both exist. Again, x would need to be a value in the domain A intersection B so that we know that both of those have valid meaning. Similarly with multiplication, we'll just write fg of x, and that would mean that we're taking f of x as the value multiplied by g of x. Again, x must be a value in both A and B, which is A intersection B. Last but not least, we get to the operation that causes us the most headaches, f divided by g of x. Now, as you can probably predict, this is equivalent to f of x divided by g of x. However, we have to be a little bit more cautious with the domain, because there are probably some values of x that when we plug them into g is defined, but f over g would not be defined because perhaps g of x equals 0. So the domain in this case, we'll have to make sure that x is a value in A intersection B so that we can compute f of x and g of x, but with the exception that we have to exclude values of x where g of x equals 0. And again, there could be multiple values of x where g of x is equal to 0. So we'd have to remove all of those from the domain. Okay, well, let's come up with a couple examples of f and g. And then instead of having to draw these circles to represent sets, what we call a Venn diagram, we can actually indicate the domains on a number line, and we can look at the intersection as the overlapping intervals of a number line. All right, here I've got an example of two functions, f of x and g of x. And Well, f of x, you can see, is a rational expression, 1 over x squared minus 4. G of x is a radical function, root x plus 2. Neither one of them is any, particularly boring polynomial or anything here. So before we really get started on giving expressions for these following combinations of f and g, we should really start to think about, okay, what is the actual domain of f and g first? We should factor the denominator of f and see what values are not in the domain. If we factor the denominator, we can see that we get x plus 2 and x minus 2. So we can't let x equal either negative 2 or positive 2. That means that we'll have the remaining values on the number line. We could indicate that very quickly using interval notation. Using the number line, we're going to have open circles on negative 2 and positive 2. And we'll have 3 separate intervals, and they will be unioned together to get the domain A, which is the domain of f. Now, what about g of x? Here we're going to have to make sure that we have x plus 2 greater than or equal to 0. And that means, of course, that x will need to be greater than or equal to negative 2. And we can indicate that using interval notation, and maybe we can visualize that on a number line as well. This time around, we've got a solid dot at negative 2, and we'll be shading in all of the values greater than or equal to negative 2. All right, so for the first expression, let's take a look at f plus g of x. And that is simply just going to be adding the two functions together. Now, I'm sure we could do some simplifying here. We could get a common denominator and write this as a common fraction. But for the purposes of what we're really investigating right now, let's take a look at the domain. The domain is going to be the intersection of a and b. So, taking a look at a number line, the interval from negative infinity to negative 2 is not included in the domain of g. So we'll have to omit that interval. The value x equals negative 2 is not in the domain of f. So we'll have to omit that value. That means that we'll have an open circle at negative 2. Now the interval from negative 2 to positive 2 is included in both the domain of f and the domain of g. But the number 2 is not included in the domain of f. So we'll have an interval from negative 2 to positive 2. However, it won't include the endpoints. Finally, we see that the interval from 2 to infinity is included in both of these domains. And so we'll include the interval from 2 to infinity as well. Now, this would be indicated as the intersection of a and b. And if we wanted to give that an interval notation, we would have negative 2 to 2, not including the endpoints, and 2 to infinity. All right, well, let's take a look at the expression for f minus g of x. Again, that's just going to be a very quick subtraction of the two different expressions. And again, we could simplify that and make it a common denominator in a single fraction if we wish. But it will also have exactly the same domain, a intersection b. In fact, addition, subtraction, and multiplication will all have a common domain of a intersection b. But we might have to do a little bit more simplifying when we look at products. Well, let's see, the product of f and g, and that is simply going to be 1 over x squared minus 4 times this root, this radical square root x plus 2. And of course, we could make that over 1 and write this as a single fraction by multiplying across numerators and denominators. Now, for the quotient, f over g. This time we might need a little bit more caution when we're taking a look at the domain. So, first of all, let's see what the expression looks like. We can see that we've got a fraction inside of a fraction. It's a combination of rational expressions. It might look a lot better if we were to write this denominator over 1, and then we could use the reciprocal and multiply instead. Now this will make things look a little bit nicer because when we're just doing multiplication, we can then combine together by multiplying numerators and denominators. But what about the domain? Well, here in this case, we have to make sure that our denominator, root x plus 2, is not equal to 0. Remember that we want g of x here at the bottom to not equal 0. We can then figure out what values of x will not be allowed. Setting the square root of x plus 2 not equal to 0, we see that we cannot allow x to equal -2. But, of course, well, our combination of domains A intersection B already does not include the value of -2. So there is no additional restriction here. A intersection B, the -2 to +2 endpoints there are not included. So this means that the domain of f over g of x is also just the same intervals, -2 to 2 and 2 to infinity. All right, well, let's take a look at a completely different way of combining functions. Not an algebraic way, not adding, subtracting, multiplying, and dividing. But what happens if we take, let's say, x is our input, we plug that into the function g of x, and we'll get that result. But then we take g of x as the input for another function, f. So now we have what's called a composition of function. X is put through one process first, and then put through a second process. All right, let's take a look at composition of functions. With composition of functions, we'll suppose again that f has domain A and g has domain B. I've got a very similar looking picture here. But what we're going to do in this case is, let's suppose that we were to take x and then we wanted to plug that into g. And then what we get as a result, we'll plug that into f. Well, since f has a domain A, we'll have to make sure that whatever value we pick for x to plug into g, g of x must be a value in the domain of f. So let me rearrange this picture a little bit. We'll have to make sure that g of x is a value in the domain of f. Now we have a notation for this. What we would say is f of g, and we'll write that f with a little open circle. And then, of course, if our variable is x, we would write f circle g of x. This means that it was f evaluated at the function g evaluated at x. So it's a little bit of a compound notation. It's a composition. X is plugged into g first and then plugged into f. And so the restriction on the domain in this case is we must have x in the domain of g first. In this case, x needs to be in B. And then the result of that, g of x, must be in the domain of f. In this case, g of x must be in A. Now, similarly, we can also define g of f, in which case x must be in the domain of f, and f of x must be in the domain of g. And that's just a composition in the reverse order. And we can do any functions that we like in the same way. We can even have the composition of f with itself. If you wanted to look at the composition of f with itself, well, then x must be in the domain of f, and f of x needs to be in the domain of f. Here are just a few shorthand notations for different compositions. F of g, g of f of f, and g of g. And these are what they would mean if you just wanted to write that out in sort of a normal function notation. All right, well, let's take a look at an example and see what the composition would look like. All right, well, here are the two functions again, f and g. We still looked at the same domains A and B, but now we're looking at the composition f of g. Now, remember that this means that we are looking for the function f evaluated at g of x. And we can first of all say, well, that is just f evaluated at the square root of x plus 2. Right away, you can see that we must have x is going to be a number from -2 to infinity. That needs to be the case before we can apply the function f to it, regardless of what f is about to do. See what f is about to do is actually square that. We square that square root, and then we subtract 4 from it, and eventually we take the value 1 and divide by that result. Now, of course, squaring the square root is going to cancel that, and it's going to make a very nice looking expression, x plus 2. Now that the root is canceled, we can subtract 4 and simplify. 1 over x minus 2. Now, as a result here, looking at what the function f has done to the function g of x, it seems like it's removed that restriction that x needs to be from negative to infinity. But remember, based off the order of operations, it was actually at this step here that we needed to have that restriction. So don't get rid of that restriction, but simply add another restriction here at the last step that x cannot equal to 2. And as a result, our domain would be from negative 2, positive 2, without including positive 2, and then the rest of the number line after 2. All right, well, now let's try g of x. Okay, it may look a little bit strange the first time you see that. We are evaluating g at g evaluated at x. So we're really just plugging the expression for g of x, square root of 2, square root of x plus 2, into square root of x plus 2. So we end up with the square root of x plus 2 plus 2. All right, now remember at this particular step, before we plug root x plus 2 into g, we need to have x as a value from negative 2 to infinity. Now, as a result of square rooting the entire thing plus 2, at this particular step, we also must have the square root of x plus 2 added to 2 greater than or equal to 0. We can try solving this equation. That means that we need to have the square root of x plus 2 greater than or equal to negative 2. Well, this is always going to be true. The square root of x plus 2, whenever it's defined, is going to be a real number of at least 0. And definitely this is always going to be greater than or equal to negative 2. So this is always true. And so as a result, the domain for this function will just simply be all of the values from negative 2 to infinity. And that will ensure that the square root of x plus 2 is a real number and that g of x is defined. Well, there we go. That's the algebraic operations as well as this new operation called composition, which you can't really start talking about until you have function notation under wraps. F of g is going to be a very important way to take complicated function and sort of break them down into easier functions. When you have the square root of a polynomial, well, then you just have a basic polynomial and a basic square root function that are composed together, a polynomial inside of a root. It's going to be very helpful when we're looking at calculus, when we're studying things called the derivative of a function, to see how a function might have many little components that are just composed together. And that'll be much later on, but it's definitely useful to get the hang of it now. Anyway, thanks for watching this video. I'll see you again in the next video.